And Russell is here. No Amelia and no Hannah. So I know I'm teaching super slow. I'm sorry. I tried to go faster. We're still on the Earth, right? The schedule says we're like 2 days removed from Earth. So a little behind. We'll have to catch up at some point. I like these pretty pictures of Earth. And can you see I marked Lincoln, Nebraska to the best of my ability? Right in the middle of nothing, right there. Dude, I measured it as carefully as I could. It should be straight over from that point, straight up from here, and straight down from there.
And you're still too far. You barely off, but you got that.
I'm not worried about Russell's opinion on this one. I think we did pretty good. It's a fact, he says. Okay.
What we learn from building houses, there's no almost. You want to get it right.
All right, let's move on. So we're going to continue looking at the Earth. I like this picture in contrast with the others. These are actual satellite images. You can see the clouds and the atmosphere and whatnot. You can see Saudi Arabia over here, yes. Here, well, you can also see Saudi Arabia.
That was a little bit too much to the east.
I'm not worried about it. But this one here, taking away the water, we see the surface, which is what we tend to focus on. Although if we're looking at other planets, if they had surface water, we'd be looking at it. It's just no other planets have surface water.
Europa is underground.
Yes, under ice, not surface. Okay, so let's move on. How do we know what's going on inside the Earth? It was from the seismic waves, the two types I mentioned there. We already saw these pictures. That's a very quick review. And it's when earthquakes or, as I said, nuclear detonations, those kinds of things happen. That's how they gather information about the Earth. And so, do you remember how they know there's a liquid core?
Because the S waves don't go through.
Because the S waves can't go through a liquid, and there's a shadow region in the S waves. The solid core, more complicated. How they know there's a solid core?
The P waves kind of go around it and send out.
Yeah. When the P waves get to the solid core, they send surface waves around the solid core, and those radiate P waves out. So they can see those secondary waves. Okay, so now a question about this stuff that we very quickly reviewed. Which statements, notice it's plural, are true about seismic waves? I believe the correct number is 2. It has to be true. It has to be 2. 1 in the first 3, 1 in the second 3, right? I mean, all right. Everybody has answered. We had one person that said P waves travel faster than S, and 6 that said S travel faster, and 1 that said they have the same speed. Nobody said S waves can travel through liquid. I believe that is 9-0. I believe that because, believe it or not, the last 2 are off the screen. Actually, maybe 1. I can't see this one at all, so I'm going to cross it off. It's off the screen. Yeah. See that green line you see? That's the next to bottom line. Okay, so that's it's supposed to auto set them, and I usually adjust them. Okay, so now let's look at this. Talk about the names. What does P stand for? Primary. And what does primary mean? First.
Well, not always.
No. The primary wave is the first one to get there. That's why it's called the P wave. It also has a secondary name of pressure because it's a pressure wave. So the primary wave is the first one to get there, so it's the faster one. So the one person who said, oh no. The one person who said P waves travel faster than S waves was correct. S waves are slower. The S stands for secondary, but in your brain you can say slower. And they're also shear waves. And then I assume we all got this right. Well, at least one person got it wrong, I guess. Or didn't answer one of the bottom three. Only P waves can travel through a liquid. S waves can't. Liquids can't support a shear, and so they can't have a shear wave go through. Okay, so that was key information for us understanding what's going on inside the Earth, what it's like. So here's what the interior of the Earth looks like as far as we can tell. One thing that I find very curious is once you get past the crust, the Earth is very, very uniform. That is, it's spherically symmetric. At the same height, you have the same temperature, pressure, etc. It's pretty darn uniform. How do we know that? By the seismic wave. That's the only way we know it. So everything we see here is interpretation of the seismic waves. Right? It's always important in science that you understand why we believe it to be true, not just, well, they say it is, so it must be. So what they look at is things like when a seismic wave goes into the Earth, if the speed gets faster, it does the same thing that light does when it goes into a faster medium. Do you remember what light does when it goes into a faster medium? Well, yes, it does go faster. Remember we talked about refraction, the bending of light when it goes from one medium to another. And if it goes into a slower one, it bends toward the material, toward the normal, as we say, going into it. If it's going faster, it bends away from going into it. And so as the seismic waves go deeper, the speed increases a little, we can tell, because the waves actually curve. And so they look at where the waves come up and how long it takes, and they can reconstruct the paths, and then from that determine more about the composition down there. And so, of course, you have multiple places for the waves, you get multiple pieces of information. You start building up a pretty complete story. So looking at the Earth, the outermost part is the crust. The crust, 20 to 70 kilometers is what this says, but the reality is the oceanic crust is only about 5 kilometers deep at its thinnest. And the oceanic crust is thinner by quite a bit than the continental crust. But they weigh the same. So how is it you have a thin one and a thick one and they weigh the same? Yeah, the oceanic is denser. Why? Well, the oceanic crust, and we can study that pretty well, it's basalt. It is essentially melted rock that came up, hit the water, cooled, and froze. And so that basalt is pretty dense. Whereas in continents, we have soil broken up, and that makes less dense. You have more air, more holes in it. And so that's why continents float higher, because they're less dense material. So if you were to get through that, scientists have tried. They've really tried to get through the crust into the next layer that's called the mantle. They've been unable because as you go deeper, it gets hotter. And we make drills out of metals, and the metals have a melting temperature. And so the drills start getting soft and start snapping. So as far as I know, we have still not been successful in penetrating through the crust into the mantle. But then we have the mantle, which is a reasonably thick layer. If you look over here, you have distances from the center of the Earth. So the crust is on average 6,357 kilometers from the center at the poles. It's a little bit farther if you're at the equator. And given that the thickness of the crust is somewhere around 20 kilometers, 20 compared to 6,357 is very small. So that crust, compared to the size of the Earth, is negligible in thickness. And then we have the mantle that covers around 3,000 kilometers. Almost half of the Earth's radius is in the mantle. In fact, the mantle is differentiated into the upper mantle and the lower mantle. What's the difference? Well, we have these things we call tectonic plates. And the tectonic plates include not just the crust, but also some material in the upper mantle. And those plates are like eggshell. They're cracked, and if you push on them, you can make them slide. This theory of tectonic plates is actually only about 100 years old. It's not a long, long time understood idea, but we have different pieces of the earth that are like, it's like cracked eggshell, and then things can make those move. And when they move against each other, you get higher stresses. So you may have seen over the weekend that the U.S. Geological Survey, I think it is, released an earthquake warning for Southern California. That there was an increase of 1% in the chance of them having a major earthquake. And so everybody was all flutter, an increase of 1%. With the fact that we have no idea what the odds of having an earthquake are, it doesn't make me super concerned. But it comes from studying those pieces moving against each other. So this upper portion that forms the tectonic plates has its own name. It's called the lithosphere. Litho means rock. So the lithosphere, the rock sphere, is the upper part here that forms the tectonic plates, the pieces that can move. Then you have the lower mantle. Then you get down here and you have the molten core. I'm sure no one here has spent a lot of time fighting in the molten core. But back in the day of 40-man raids and WoW, molten core was like the top raid, and we spent like 3 nights a week fighting in the molten core. So I love that, we have that. Then we have the solid core in the center, that's the center 1,200 kilometers. So putting all that together, notice the materials, the core, iron and nickel. How do we know it's iron and nickel? It's not by studying it. We haven't done a chemical assay. How do we know it's iron and nickel?
Because they're the most dense.
That's right. It just comes down to the density. We say, well, those are the most dense common materials in the earth. Hence, that should be what's sunk to the center. It's not exclusively that. Certainly things like uranium, osmium, gold, those things are much more dense than iron. But they're also really rare. So they're going to be there in higher percentages than they are up here, but still trace amounts compared to the amount of iron and nickel. So we have that solid iron and nickel core, the liquid. Oh, look, iron and nickel as well, for exactly the same reason. Then we have the mantle.
Wait, why is this inner part solid?
Excuse me?
Why is the inner part solid?
Okay, why is the center part solid? This is actually a fundamental physics question. When you increase the pressure, right, because if you go deeper and deeper, you have more and more weight that it's having to hold up. So the pressure is much higher down there. You increase the pressure, things tend to go into the solid form. Now, can anybody name an anomaly that doesn't do that? No? Water.
Yes, it does.
Water does that at very high pressures. But if you take water that's at its freezing temperature and compress it, it will actually melt, which is the opposite of what most things do. Water is very unique. And like water expands when it freezes, which causes us problems like breaking pipes in our homes, but also allows us to do things like live on Earth. So we're kind of happy about that. Because if water didn't expand when it freezes, well, let's talk about what it does. You get cold. Let's say you're up in Minnesota. It gets cold. And so you form little ice crystals in your lake. They float to the top, and you form an ice barrier on the lake. That ice barrier is a good insulator. And so the water underneath, it's much harder for it to freeze because it's hard for the heat to get out of the water below so that it can freeze. And so you end up having a layer of ice, maybe this thick, but then you have water underneath, so the fish are good to swim and whatnot. If it went the other way, if water was a normal material, and when it froze, it contracted, it would sink. And then you would have the top would refreeze and sink. Refreeze and sink. And you would completely freeze your lakes every year in Minnesota if water did the opposite thing. Also, the fact that it freezes makes the lake more reflective, which in turn allows it to reflect more sunlight. There's a lot of things that go into God tuning our universe or our Earth to make it so we can live here.
I mean, we have to compensate that with water facing and everything. When you're building like a building, you have to go below the flash point. People all say it's gonna.
Yeah, it's going to buck.
It happens quite often when people are like, "Well, it's just simple. I'm just gonna do it by myself."
That's because the foolish man builds his house upon the sand. The wise man.
That's when I built in New York City, where it's bedrock, but at the top.
For the record, the wise man does not build his house below sea level and then just build a levee, i.e., New Orleans.
So I found that apparently in New York City, most of the cities built on bedrock, except for that one part when they expanded out.
I mean, Jamaica Plain is underwater right now.
Okay, let's get back to this. So we've talked about the layers of the Earth. We have an understanding of these layers based on our seismic waves here, and then we use this to look at other planets and compare. Are they like Earth or are they different? How are they different? Why are they different? So we just talked about the pressure inside the Earth. Pressure is high because you have the weight of everything pushing down. The core of the Earth is also hot. Hot for two reasons. Reason number one is that compression. When you compress things, they get hot. Just think about a bicycle pump, right? You have a bicycle pump, hand pump. As you pump it up, you can feel the barrel of that pump gets hot because you keep compressing the gas. So in the Earth, because of the weight of material as it formed, it compressed and got very hot in the core. And over time, that thermal energy will escape. So the core should be in a general cooling process, cooling off from the initial energy that made it hot when the Earth formed and it got crushed. But then there's the second thing. The second thing is radioactive decay. We talked about radiometric dating. In the Earth, we have things like uranium, very long half-life. Uranium's half-life is measured in billions of years. And so the uranium isn't going anywhere, but we have enough of it that we have energy coming off each time it decays. It gives off energy because it's gone to a lower energy state in the nucleus. And so that energy is heating up the Earth as well. My brother just watched The Martian, and apparently he just took plutonium and used it to keep himself warm. Generally not a good plan, because of course you're going to be bombarding yourself with these particles that are heating up the air, and it's not good for you. So the center of the Earth, we believe to be somewhere around 6,500 kelvins. How does that compare to the temperature of the photosphere of the sun? The sun is about 5,800 kelvins. So the core of the Earth is hotter than the surface of the sun, which when you put it that way, it's pretty impressive. Now the core of the sun is somewhere in the ballpark of 15 million kelvins. So it's nowhere in comparison to the core of the sun. Question, Russell.
The corona of the sun?
The corona of the sun goes back up to around 1 million K. It's an interesting fact that we'll get to when we talk about the sun.
Isn't lightning hotter than the surface of the sun?
The gas would be, yes. Now, some things about cooling. The cooling rate is going to be proportional to the surface area. So a bigger object has a bigger surface, and thus it can emit heat faster. A smaller body with a smaller surface doesn't emit it as fast. But in terms of the energy content is proportional to the volume of the sphere. So volume of the sphere, the equation for volume of the sphere is 4/3 pi times radius cubed. So the volume is proportional to the radius cubed. The surface area is 4 pi times radius squared. So the surface area is proportional to radius squared. So I'm just going to write the equations here. Surface area is equal to 4 pi times radius squared. And the volume is 4/3 pi times radius cubed. So the rate of temperature change is going to be proportional to the rate it cools divided by the total amount of heat it has, or its volume. And so if you do that, you have the surface area 4 pi radius squared divided by the volume 4 pi radius cubed over 3. The rate of cooling is proportional to, well, it's 3 over the radius, but who cares about the 3? So the rate at which something cools down, the rate at which the temperature drops, is proportional to 1 over the radius. So bigger radius cools more slowly as far as the rate of the entire thing cooling. Even though it's giving off more energy, so there's more heat leaving, it has so much more total heat that it's actually cooling off slower. So big things like the Earth should cool more slowly. Small things like Mercury or the Moon should cool more rapidly. So when we look at Mercury and the Moon, we should expect them to have a lot less molten core, if they have any at all, because they could cool much more rapidly. Does that logically hold together to you? Yes and maybe are the two answers I'm getting. A cool thing to understand, this is really important when you look at the sun, is convection. You probably heard of something like a convection oven. Convection is one of the 3 methods that heat can transfer. That is, energy can move from point A to point B without doing work. The 3 methods, and I'll go through all 3 here. The first one is conduction, direct contact. That is, if my hand was at 500 degrees Kelvin, if I touched him, it would burn him because of the direct contact. That's the first one. Would I have to touch him to burn him?
No.
No. Why not?
Just being close.
Being close is enough because there are 2 other mechanisms. The second mechanism is the one we call convection. Convection involves an intermediary. So if I take my hand and it's 500 kelvins and I put it below Russell, it's going to heat up the air. And what does hot air do? It expands first, and because it expanded, it has less density, and because it's less dense, it floats up. So hot air floats. People always say heat rises. It's not the heat that's rising. It's hot material expands and floats upward. So hot materials rise. So that's called convection. When I heated it up and it moved, and so it carried the energy away through the intermediary. And so like if I use a Bunsen burner, Bunsen burner, obviously if I put my finger in the fire, ow, it hurts, right? If I put my hand above, ow, it still hurts because of convection. And then the third method, back when I was a kid, we still do this actually. We go and we spend a weekend out of Yosemite. We used to spend a whole week before the weekend, so we did more time. We have one of my uncle's classmates from Monterey Academy bought a big area just outside the gates. And so we lived there, we stayed there for free. Very cool. And so we would build these huge fires, what we derisively call the white man fires, because we said, the Indian is wise. He builds a small fire and he comes close and heats himself up. The white man builds a big old fire and has to stand way back.
I understand that with that.
It's kind of fun. It'd be like cold out and it'd be crispy on the side facing the fire and cold on the other side, kind of like rotisserie to keep the temperature normal. Well, the last method is radiation. That is actually electromagnetic waves coming out of something because it's hot. Now, we've already studied that. We called it incandescence before. So radiation, incandescence are really the same thing. So that's our third mechanism for heating. The sun heats the earth. Which of those 3 mechanisms do you suppose heats the earth? Which one?
Radiation.
Radiation. It's the electromagnetic rays, the waves coming from the sun that are heating us because it's hot. On the other hand, if you look at the surface of the sun, it looks kind of like creamed corn. It has these things that are called granules that appear and disappear. And looking at them using a Doppler shift, what information can you get from a Doppler shift? You can get the direction of motion if it's coming toward you or moving away. They see the centers of these little things, called granules, are moving toward us, and the edges are moving away from us, back into the sun. And the centers are hotter and the edges are cooler. What's going on? Hot material in the sun is expanding and floating up to the surface, gets to the surface, it cools, and sinks back down. So convection is causing this effect on the sun. So here we're talking about convection because convection is also one of the important things that's going on in the core of our Earth. So you have the hot core that heats material, that heated material expands and rises. And not only does it occur in the core, it also occurs for things like the Hawaiian Islands. The Hawaiian Islands are an example of what we call a hot spot. There is essentially a convection current that is coming up from that molten core through the mantle and comes up in Hawaii. And where it comes up, it causes a volcano. Now, this kind of volcano, we say it forms a shield volcano, the kind of magma, the kind of lava, when it gets to surface, we call it lava instead of magma. The kind of lava it produces just flows nicely. And so all of the Hawaiian Islands, the entire chain, is actually one hot spot with the crust of the Earth moving over that hot spot. It punches a hole here, and then goes a little more, punches a hole there. And each of the Hawaiian Islands is simply where it punched a hole through the crust as the crust moved over that hot spot, which I think is really interesting. Now, where's another hot spot? Direction's right. Let's see, that's north, right? That's west. Over there, there's a hot spot. What's over there?
What are you pointing?
I'm pointing northwest.
Yosemite.
I wish.
Yellowstone.
Yellowstone. Yellowstone is also a hot spot.
You mean the super volcano?
Yes. Yellowstone has in the past been a supervolcano and probably will again erupt being a supervolcano. It has a really big magma dome underneath it. That's why you have all of the hot springs and everything and the geysers, because you have a hot spot being heated from the core.
I know it's a hot spot.
We're in the second ash spot, by the way. There's that area.
I remember looking at all of the different ash. I don't know if you guys have ever been to Asphalt. It's pretty good. It's a pretty long drive from here, but it's pretty cool. It's a place where they found a bunch of animals that were buried in the ash from Yellowstone's eruption.
I know it's not a good hot spot.
Where's that?
Mount Etna.
I cannot confirm nor deny.
Sicily.
Yeah, I've heard of Mount Etna, but I cannot confirm nor deny that it's a hot spot. Another thing these currents do, those are the primary drivers for plate tectonics. Plate tectonics is the motion of the plates, and it actually turns out the motion of the plates starts at what we call the mid-oceanic rifts. What's a rift? Well, the rift zone, besides being a very interesting book series, I read when I was, 10.
It's Iceland. Iceland.
Okay.
No, Iceland's a rift zone.
It might be. That's not what I'm talking about. A rift zone is a place where magma is coming up and creating a separation. So that magma comes up between plates and it's like my picture of Samson pushing out to, collapse the balcony and kill himself along with.
That was how the needle was made.
What's that?
That was how the needle was made.
Maybe. I don't know.
No, that's how it was.
Okay. So we have these mid-oceanic rifts where magma is coming up and pushing plates apart. Pushes those plates apart, the magma comes up, water's cold, water cools it rapidly, it freezes and forms new ocean floor. So basalt, the kind of rock that we have in the ocean floor, is actually the result of this rifting process. The magma comes up, freezes, and forms the new ocean floor, a dense rock that was frozen relatively quickly. If you freeze the rock really, really quickly, it freezes so quickly that it doesn't have time to form any crystals. And we call it glass, and it doesn't have crystals. So it forms a glass obsidian. So obsidian is just super rapidly frozen rock. If it cools a little more slowly, it grows little tiny crystals, and we call it basalt. If it cools really slowly, then it forms big crystals, and we call it granite. Now there's lots of different types of rock in between. You have your gabbro and your, whatever. But those are fundamental differences in the rock as we understand them. When we get to talking about the moon, we'll look at the type of rock to compare it to what we see on Earth. Let's see how many slides I've talked through. Here's a picture to show us the way the mid-ocean rift works. You have rising material pushing them apart. Notice the speed, about 20 millimeters per year. How far is 20 millimeters? Okay, let's take our hands and put hands or fingers so they're about 20 millimeters apart in your estimation. I'm waiting to see people do it.
Oh, 2 centimeters.
It's exactly 2 centimeters. So 2 centimeters is just under an inch. 2.54 centimeters is an inch. So it's about that big. That's how far the ocean is moving apart while each side is moving. Doesn't seem very fast, but over the course of a decade, you have, a good 6 to 10 inches of motion that you will have. I worked for a summer acting with a theater in Skagway, Alaska. And one of the things that was actually the coolest thing to do in Alaska, or Skagway, was going over to Dyea. You guys all heard about Gold Rush, right? The Alaska Gold Rush specifically? Well, the Chilkoot Trail, where they had to climb up over the mountain, it actually started over there at Dyea. Dyea had the misfortune of not having a deep water harbor, so it's hard for the ships to drop them off. Skagway has a deep water harbor. But anyway, I went over to Dyea. Ranger gave a great talk about the local geology. And one of the things he mentioned was because of the ocean coming in, now the ocean is more dense than the continental plate. So when the two come together, which one's going to sink under? Right? They can't just sit here and stop. One has to sink. Which one's going to go under? The more dense or the less dense? The more dense. So the ocean goes underneath, so that basalt slides underneath the continent. But what does the continent do in response? It buckles up. And so Dyea is now more than a foot higher in elevation than it was in 1849 at the height of the gold rush, just because of this action. And if you look at the coast, the Alaska coast, if you ever look at the islands, you see the islands look like little thin things. And that's because it's kind of like me making pancakes. I've got the pancakes and I take the spatula and I go to scrape them off and it squishes them up into long, narrow things. That's what's happened to make those islands. You had material that was on the ocean floor that got scraped off as it subducted under the continental plate and made those islands. Question?
Everest is good.
Excuse me?
Everest. The mountains.
Mount Everest? What about it?
They're getting taller.
Yes. Yes, Mount Everest is, okay, you know I'm a creationist, right?
Yeah.
There was a creationist that came to speak when I was at PUC, and he was talking about the rate at which mountains erode, because, of course, you have erosion that occurs. And, I said, at this rate, there should be no mountains left if the Earth is millions of years old. And my colleague, the physics professor, afterward came up and said, but what about the mountain growth? And the guy looked at him like he was speaking in a foreign language. What? Mountains grow? Yes, mountains grow. They grow because, again, of this action. The whole Rocky Mountains are believed to be formed because of the Pacific plate subducting, that means sliding underneath, the North American plate, and then causing buckling all the way out in Colorado from California where the initial subduction was occurring. What else occurs when you have one plate sliding under another? Okay, earthquakes, because clearly you're going to be stressing the ground. The difference in a fault and a plate boundary is just how big the crack is. Faults are like complete cracks, plate boundaries are like complete cracks and faults are partial cracks. And so you build up more stress from that subduction, makes more stress on the little cracks, and when they slip, you get an earthquake. Okay, so that's one thing. Another thing what I was looking for was grinding. Not grinding, as Polly Shore would say, but grinding. You have something sliding underneath and it's grinding rock. Well, what happens to stuff when you grind it?
It gets powdered.
It gets what?
Turns into powder.
Turns into powder, true. Temperature-wise, it gets hot. because you're converting that energy and motion into making things hot. And so you tend to melt a lot of rock where you have that subduction. So looking over here we can see the subduction. It's sliding underneath. And so that's going to cause things like that. And like this. Volcanoes. That sliding causes so much heating that it melts rock. That melted rock is less dense, floats up, and makes a volcano. Which leads us to the ring of fire. Because it burns, burns, burns. That ring of fire. What's the ring of fire? The ring of fire is a boundary around... Don't laugh, Latif. It's a real song, man.
Look, you can see Iceland. It's like unbelievable things.
It's a ring of volcanoes that goes around these mid-ocean trenches. And so we have all these volcanoes because we have ocean plates subducting underneath the continental plates.
Indonesia has a bad time.
And not only does it create volcanoes, it also creates earthquakes. So anywhere here on this ring of fire, you're likely to have lots of earthquakes. Where do you have the biggest, baddest, most common earthquakes in the world? No, there's another place where they make not Japan, although that's a pretty good guess. They have some significant things there. The biggest, baddest occurs down here. I think that's where Chile is.
Chile.
You call it your way, I'll call it mine.
I found out something. Apparently, Hawaii has the world record for like most amount of tsunamis that hit it.
That's lucky of them. So the reason they have all of the earthquakes is because of being on that ring of fire. One could guess, the motion of the Nazca plate might be a little more significant than the motion of the Pacific plate. Up here, you can't see it, but you have the Juan del Fuca plate up here that moves around, causing things up there in Washington like it's, Mount Hood and Mount Rainier. All of those are volcanic because of the subduction there. Excuse me? Yes, Mount St. Helens. How could I forget that one? Now, something that's cool over here is there is one rift zone that's not in the ocean. The Great Rift Valley. Actually, it probably is this whole thing. The Great Rift Valley is the only non-oceanic rift zone. It's a place where it's being pushed apart, but it's not actually formed. The basalt, this low level, so fills in with water. So there is one place where you can study rift zones without being underwater. And where's your home? Geographically, it's inside that, isn't it?
Yeah, right at the bottom of the lawn.
So right out there. So ask Tioni, what's it like in the Rift Valley? Because I don't know. But I lived over here, man. There ain't nothing over there. Yeah.
So does that mean, given enough time, many years, that little section would be pushed apart from the rest of Africa?
Likely, yes.
Okay.
So it would be like India.
India is actually really interesting. Whoops. India didn't make. Okay, here it is. If you watch pictures, which I didn't load it up. I had it loaded up for class last time. Very optimistically thinking I'd get there. Video of the motion of the plates. You see that India was really interesting. Like all these plates are moving around slowly, and then at the very end, India was like down by Antarctica, and it just goes zooming up and smashing into Asia, which is why it's called the subcontinent. It was like its own thing that merged with Asia. Okay, interesting things about these rift zones. Sailors noticed that as they were sailing over the ocean, their compasses were doing crazy things and unreliable. And so, remember, we're scientists in this class, right? In this class, we're doing the scientific method. You clearly notice something interesting there when your compass isn't working. It's pointing random directions, it seems. So scientists are all, must be something magnetic, let's go study. And so what they found was, frozen in the ocean floor is magnetic orientation. That is, we have rock, hematite, it contains iron. And that iron can form permanent magnets. And so when you have molten rock, when it's melted, if you have a magnetic field present, the magnetic dipoles are going to align with the Earth's magnetic field. But then they freeze and they stay that way. And so the ocean floor has alternating magnetic fields frozen into the rock. It's exactly the way information was stored on cassette tapes. You guys are way too young to have to deal with those. It's also exactly the way that information is stored on a hard drive in a computer. Not on an SSD, not on optical drive, but on an actual hard drive. They store it by putting in different orientations of magnetic fields in their media.
Some of us take these cassette tapes a long time.
Nice. Because, I'm of the age when, you like a girl, you make a special mixtape, you give it to her, here, listen to this.
VHS tapes are horrible.
Yeah. Okay, so looking at the ocean floors, you can actually see a history of the Earth's magnetic field. So this is illustrating black is one direction magnetic field, white is opposite direction. And the Earth's magnetic field,
Is north.
well, it says white is reversed, so black would be pointing north. Yes. So if you look at this, you can see that the Earth's magnetic field apparently has reversed over and over and over in time. In fact, the average time for reversal of magnetic fields is somewhere around every 200,000 years, the Earth's magnetic field changes polarity. What was the north magnetic pole becomes the south. What was the south magnetic pole becomes north. Which, of course, is fodder for many movies, right? Whoa.
What's that? What was that movie? The Day After Tomorrow?
I don't know. I've seen at least 3 movies that have that as a major theme.
No, Day of Tomorrow was like some other one.
I can't remember which is which. But we have this information stored about the Earth's magnetic fields. And so then we have to start wondering, well, where do the Earth's magnetic fields come from? And this is the video. Oh, I can type that. Who can remember UWWW UTTNTIO? Who can remember that? Glad everybody said, oh, yeah, somebody else. You think so?
Hey, look, there it is.
Yeah, there it is. Because I did have it last week to show you guys.
I feel like I shouldn't. I feel like I looked at this.
Well, I've got the sound turned off.
Why does that look like
This is sound coming from this. Okay, it's just kind of cool. What was your question? I don't know. Okay, so this is showing, notice we have time down the lower left. MYA means million years ago. So this is what scientists believe the Earth looked like 2 billion years ago. And so we have here a supercontinent called Atlantica. They just give it a name. There's no one there to name it, so why can't we name it? And as we go forward in time, we'll start getting to things that you might recognize. This is all under the motion of plate tectonics. So now we have our supercontinent of Columbia. Keep going. Not recognizing much yet, are you? Yes, I think I can pick out California.
what is that?
Breaking apart again. Now, if you believe that life evolved you have, at this point, nothing more than bacteria. We watched a lot, right? Another supercontinent of Rodinia. Looks like the Aleutians on top, right? Now, according to the fossil record, the Cambrian explosion is about to occur. That is, it's about to go from not very much to the entire spectrum of life right out here. And we have the supercontinent of Gondwana. Okay, so clearly we didn't have anything recognizable because we have nothing recognizable here. But we're getting close now, and we will start to see things you can recognize in the big ones. Pangea, you may have heard of Pangea. That's, I believe, the last of the supercontinents. And from this, you can start seeing South America, North America, and Africa. You guys see all together. When I was a little kid reading those encyclopedias, I noticed that Africa and South America looked like they could fit together. And that was one of the keys, I believe, for Wegener with his plate tectonics theory. So now where's India? Well, this one didn't show the Great Motion of India. Usually has India flying up there at the end.
If I think anyone's a supercontinent, it's probably Asia, Africa.
Now we watch that. Is this just fanciful? You know, here's some cool computer animation somebody could do.
Maybe just
Okay, maybe it's just educated guess. What would give them any inkling of how to make this educated guess? Okay, that was what gave the first ideas for value with the plate tectonics theory, that the continents look like a jigsaw puzzle. But it comes down to looking at that, those magnetic fields frozen in the rocks, the paleomagnetic fields. This entire thing is put together by interpreting the magnetic field stored in older rock. Is it perfect? Almost certainly it's full of errors. But it's a general idea based on what we can tell from the magnetic fields in the rock. So did we finish talking about the Earth? No. Let me finish by talking about the Earth's magnetic field. The Earth has a magnetic field that makes it look like it's a bar magnet, with the north magnetic field at the South Pole. Now that seems wrong, right? People noticed that if you had a magnet, one side would point to the North Pole, and so they called that the north-seeking pole. But then they further learned that north is attracted to south, that opposites attract. And so the north-seeking pole is seeking the south magnetic pole of the Earth. So in the Earth, if this is the North Pole, then it's the south magnetic pole. Now notice something here. It marked the magnetic North Pole, which is the south magnetic pole truly, is not at the rotational axis. It's off. And it moves. It doesn't stay the same place. You could go and you could measure very accurately and say, this is where the south magnetic pole of the Earth is. And then you can have a big party, drink all of your lemonade, go to sleep, wake up the next morning, and say, well, I'm just going to confirm my measurements. Uh-oh, it's like 2 miles over there. Right? The Earth's magnetic North Pole moves. And so in trying to understand what's making the poles, we have to take this into account that it's not a fixed location that it moves. And so the answer that scientists have come up with is, we also have to keep in mind that it flips. So once again, it's not like a fixed thing, it flips. So they have what they call magnetic dynamo. Inside the Earth, we have flowing magma. Yeah, I missed. Oops, that's our question to end the day. We have flowing magma that's going in a circle. And as it goes around circle, you have convection, it's conducting material. You have those three things. It has to have rotation, it has to have convection, and it has to be conducting material that will make a magnetic field. And we believe that's what makes the Earth's magnetic field. And when the magnetic field flips, it's because things in the center have gotten all out of whack. And we'll study more about that later. I guess I won't do the clicker question because I'm already a minute over.